Right. The next talk is from Professor Charles Elliott from Warwick. This is the Rothschild professorship. It's I understand it's funded by the Rothschild, as you can tell. Unfortunately, the director is not here to tell us the history of the Rothschilds. I'm sure it's a prestigious. Every research program has one fellow, and our fellow is Charles Elliott. For me, it's really a pleasure to introduce him. I met him in 2002 in Brunel. I'm not sure if you can remember, but as usual, he asked me a question after my talk, and it got me to think about surfaces, and I started to work on surfaces. And I should really say he's a pioneer in the area, many areas, but I think one area is that of geometric PDEs, phase fields, and so on. Charles actually was the person who hired me at Sussex in 2006.
Good move. Good move for Sussex.
Yes, yes. So he brought me to Sussex, and a year later he left, as you can imagine. Went to Warwick, but it's really a pleasure to have him here, give us a talk. I think there's lots of potential in terms of the models. We always want to be able to describe experiments in a sort of physically relevant form and to validate them to some extent. I think when you have models, can you prove convergence? Can you prove these things are of interest to him? So, as I said, he's a pioneer really for surface PDEs. If you are interested in them, in geometric PDEs, in phase field models, and so on. So it's really a pleasure to have you here. And
all right, thank you. I'm a mathematician. This doesn't sound as if it's on, does it? It is. Okay. I'm a mathematician. I was trained as a numerical analyst, but I've always been interested in applied problems, and I've always been interested in nonlinear partial differential equations. So the point of view that I'm taking today is that we want to solve partial differential equations in time-dependent domains, which are quite complicated in some way, and we like to do it in a way which is consistent with mathematical analysis. So the computations will be computation should be analysis-based. So the topic is analysis-based computation, partial differential equations in evolving domains. I'm not going to talk about all methods for solving PDEs in evolving domains. There are many, many methods. I want to talk about the situation where we approximate the domain by a union of finite elements. So I'm going to talk about evolving finite elements and evolving triangulated domains. And because the domain is changing, because we've got an evolving triangulation, we will also have evolving finite element spaces. And then we will be interested in how we would use evolving finite elements to solve a PDE. It will depend upon the mathematical formulation. And from my perspective, this is important because I'm standing here as a mathematician rather than as a modeler. The formulation of the PDE problem will lead itself to a numerical method, and we will be led to try to do some analysis of discretization. I will allude to all of these, and I will show some computational examples. Actually, it would be quite nice does anybody have a pointer, an electronic pointer?
there was one somewhere, one on the table. Yeah, it's on the table.
Okay. Thanks. Yeah. So the kind of objects that I'm interested in are hypersurface. The hypersurface, we can think of the hypersurface as bounding a bulk domain omega. Actually, we can also think of a bulk domain omega as a flat n+1 dimensional hypersurface with boundary in a higher dimension Rn+2. And that's convenient because it will allow us to treat surface finite elements and volume finite elements in the same way. I don't want that happening. Let me just maybe. Right, of course. Stupid.
There's also a stick. You have a stick at the if it doesn't work.
That's fine, thank you, Anatila. Yeah. So this is the kind of setting. We can think of these as complicated domains. We can see, if we think of this as a cross section of a domain like this, we see that we would say this is a surface. So this blue and red, what we can see on the outside is a surface, and in the interior is a bulk domain. We have a boundary. We can think of these red regions here as being very thin, and we can see there is a boundary between the blue region and the red region. We can think of that as a free boundary and an interface. So we're interested in hypersurfaces, we're interested in bulk domains, we're interested in interface problems, we're interested in interfaces which are unknown and which move. And we can see that we are also going to be interested in geometric equations because we can see that there may very well be surface energy associated with these, with whatever we're looking at here, which is these famous images of giant unilamellar vesicles. We can see that there's going to be line energy separating blue regions from red regions, and we can see there's going to be surface area giving the overall surface energy giving the overall shape. And we're interested in energetic surfaces and interfaces. Because we're interested in energetic surfaces and interfaces, and then we're going to minimize energy, then we're led to geometric quantities because the first variation of the area function is the mean curvature. And if we have more complicated energies, then we'll get other geometric quantities. We will be interested in coupling equations for the surface and on a surface to equations in the bulk. And because we're interested in nonlinear PDEs on the surface, that is, surface processes will be modeled by nonlinear PDEs, will be led to free boundary problems on a free boundary, which we can see in this picture here. We see that we don't know where this boundary is, we don't know the overall surface, so the problem is to determine the overall surface and the free boundary. So we would like to formulate these types of problems in a way which will allow us to do analysis-based computation. And of course we've seen many movies today. This is just one example. So from the perspective of this program, we know that there is complicated geometry. Now I'm not going to model these processes. What I'm saying to you is that if you wish to do simulations of moving cells, then it may very well be that you will need to be able to solve partial differential equations in complicated evolving domains. And that's the domain of the talk, not modeling. So here's an example, this comes from somewhere else. This is a computational solution of a surface dissolution. And this is a triangulated domain. This you don't see the triangulation here, but this started out as a uniform triangulation of the square. And there is an evolution process which gives the partial differential equation for the surface, and on the surface there was a nonlinear partial differential equation which is linked to the evolution of the surface, and this is the evolution. And increasing the dissolution rate in this example, we go from that kind of simple pit to something which is much more complicated. So our idea is that we want to be able to formulate partial differential equations to describe this and to formulate numerical methods based upon these partial differential equations to simulate this. And in this talk, we're going to use a direct discretization of the domain. We're not using phase field, we're not using level set. Well, we will use phase field a little bit, maybe. So what is involved in analysis-based computation? Well, what we should be aware of, there have been fantastic developments in numerical analysis and fantastic developments in what we can do computationally and fantastic developments in the mathematical analysis of nonlinear partial differential equations. So it seems that we should use these advances in the way that we do the modeling. So modeling is not, when I started doing research in applied mathematics, models people used to solve one-dimensional models. They solved partial differential equations in the square, and then 3 dimensions was quite difficult, a linear partial differential equation. Finite elements, of course, allow us to consider more complicated situations. How you formulate the partial differential equations will lead to a different type of analysis, mathematical analysis, and also a different type of numerical analysis. So we have to bear that in mind. In our context, that is PDEs in evolving domains, one could use a parametric approach, which would mean we replace we actually go for the domain, or we could use implicit surface methods like diffuse interface or phase field, or we can use unfitted finite elements, and I'm not going to talk about these, but to talk about what I call based upon parameterizations of the surface or domain. So we want to develop numerical methods. We will do analysis of discretization, and there's a lot of work necessary in analysis of solvers, and we have to implement. In the end of the day, we want to simulate, identify parameters, predict, and control. So, so related to that, those pictures of the vesicles earlier on, then we have this mathematical model. This mathematical model is an equation for the surface, and it's an equation for an order parameter on the surface, which tells us, in this instance, the blue and red regions. So this is a very complicated equation, but nevertheless, we wish to be able to solve it in a mathematically well-posed way associated with a rigorous formulation of the equations, even if we cannot prove very much about this parabolic system. If you look at this equation, you can see that it's a 4th order equation. This h is the mean curvature of the surface. Laplace gamma is the Laplace Beltrami. This is like an Alan-Kahn equation, and it's kind of modeling phase separation on the surface. So the upshot of this would be that we would replace, this is a triangulated surface, and we have to solve that 4th order highly complex partial differential equations to find that surface. Meanwhile, it's coupled with a nonlinear PDE on the surface. And in this instance, the idea was we wanted to compute a stationary configuration, an energy minimizer. And so these equations that I showed you on the previous overhead was a geometric evolution law for the surface and a PDE on the evolving membrane surface. And in this instance, this was gradient flow for a complicated nonlinear functional. The nonlinear functional was basically the Helfrich functional plus a Ginzburg-Landau functional in order to simulate line energy. Well, this is okay. If I was to these are tough equations. We're not going to, at the moment, we're not going to be able to at the moment we're not able to analyze these completely, but what we can do is to analyze and do rigorous mathematics on model equations related to these. So I'm speaking in very general terms because this is supposed to be a public lecture. So there's people know more about these things than in this audience than the public. Anyway, aim of numerical analysis. The aim of numerical analysis is to derive numerical in this context is to derive or develop numerical methodologies for interface and free boundary problems involving surface and bulk PDEs. And they should be based on a discretization of fit-for-purpose PDE formulations. This may depend upon application requirements. In this instance, I'm just going to talk about evolving finite element methods. But there are many settings where you might want to use diffuse interfaces and phase field. Generally, we want them to be consistent and stable. And that's often we're able to prove consistency and stability for discretizations for very complex systems, even if we cannot prove convergence. By convergence, I mean that we're interested in the question of whether, as we reduce the mesh size and time step, that our numerical scheme has a solution which converges to the solution of the underlying PDE. Often in this field of numerical analysis, we often illustrate by simulating simple but significant model problems. And it may be that we can only carry out the error analysis for significant model core problems. So why the finite element method? Well, what is the finite element method? The computational domain is a union of elements. It's approximating. If suppose we know the domain, then it would be some kind of interpolation. It would be based upon a union of finite elements. So we can handle curved boundaries. It can handle domains with boundaries not parallel to the axis, which is why we use finite elements. One of the reasons for using finite elements. So that means we can look at complex domains and we can look at evolving domains. If we have such a decomposition of the domain, then we can construct in a natural way function spaces which approximate the function spaces needed for the well-posedness of the partial differential equation. This is the way a mathematical person would speak about discretization. An engineer would speak about it in a different way. But the mathematical person thinks about having a partial differential equation posed in a rigorous mathematical setting, and then we approximate the various things which are in that formulation. So in the finite element method, it's natural to use a Galerkin method in the variational formulation. So the upshot will be, in some sense, natural, well-defined schemes. And then we go on with analysis of discretization, if we can, stability, convergence, and that usually follows from trying to mimic the analysis of the partial differential equation. And then we go on to the development of software. So this is triangulation of a surface. So our computational domain would be, we can think of this triangulation as being an interpolation of this surface. So it's a union of triangles. And on this, we can define a function space on this surface by using finite elements. So on each triangle, we suppose an element of our function space is a linear function, and it's defined by its values at the vertex of each triangle. So that's what we call a piecewise linear nodal basis function. We can do the same for, we can use quadratic elements if we're willing to use isoparametric finite elements. So this is a flat triangle, and this looks a little bit like a curved quadratic triangle over the flat triangle. An interesting thing about surfaces and domains is the concept of velocity. The domain is changing in time, so there must be some velocity. But what defines the change of the domain is the normal velocity. So if we're thinking of a surface, if we want to have the motion of a surface, we just need to know the normal velocity to define the surface. And we can think also, if we have a bulk domain which is changing, and when I said the normal velocity is 0, the bulk domain is a flat hypersurface in one space dimension, but now we've got a boundary. And then we define the shape of the domain by knowing the co-normal velocity. Okay. That in the context of the usual bulk space, it just means the normal velocity of the domain. Of the domain. So the normal velocity is sufficient to define the hypersurface, but in applications there may be a physical velocity which is there may be a tangential vector velocity, and we may want to, that will appear in the partial differential equations. However, if we want to get a good mesh or a good discretization of the surface, it may be that what we need is a different velocity to move the vertices of the mesh, which is nothing to do with the physical, which has got nothing to do with the physical velocity. So this is what leads to so-called ALE approaches, and then you would have a tangential velocity which defines a parameterization. We would like to use the possibilities of choosing a tangential velocity which will be useful for discretization. And I can see that I'm not going to make much headway with my all the slides. So this is an example. This surface has got a boundary. It's moving in the normal direction given by mean curvature. And as you can see, the triangulation on the left is actually developing. It is not so good. It's been moved in the normal direction. In this picture here, it's the same evolution. It's motion by mean curvature. What I mean by that is the normal velocity of the surface is given by the mean curvature at that point. We have some numerical method for doing this simulation. This numerical method is due to Gerd Zuck. And we can see that maybe it's useful to have tangential velocities to get a good mesh. Oh dear, where is it gone? Is it here? No, it's not there. Right. Ah, thank you. Success. That's the problem with doing ad hoc things. Yeah. So here's an example of this, this vesicle problem, and then this is the kind of thing that we so we're solving a kind of a Helfrich flow coupled to a phase separation process on the surface. So we have to calculate the vertice, we have to find where these vertices are, and we have to solve this parabolic equation on the surface. And that's the kind of thing that we do. Yes?
They both describe the same physical process?
Yes, as I said, this. Yes. Because this tangential. You're asking me about the tangential velocity. It's an arbitrary. It's just a tangential velocity which gives the motion of the mesh.
In some situations, for example, if you have a tangential flow,
that's why I want to. Yes, sure.
Have this movement, and you need to remesh your domain.
I said in applications there may be a physical velocity, and I'm saying that the physical velocity appears in the partial differential equation. It might also appear in the definition of the shape of the domain. That means it's going to give the normal velocity or the co-normal velocity in the way that I described it. But the mesh is constrained by the normal velocity so that you're actually discretizing the shape, but the vertices of the mesh within the domain can be moved arbitrarily. You just have to make sure, of course, that your discretization scheme reflects all of this in a proper way. So what's needed is that we need to construct our computational domains. So if we have a known domain, that's mesh generation. Unknown domains, then we may have to have surface geometric evolution equations. We need to construct finite element spaces, and then we want analysis of discretization and implementation in such codes like June or others. I'll just quickly so there's a lot of work on these types of problems. Here are names of authors who've worked on so-called trace methods, surface finite element methods, unfitted finite element methods, mesh adaptivity, moving mesh methods, phase field methods, level set methods, immersed boundary methods, etc. These are just some references of work of myself, postdocs and students and colleagues. You can find these. You can find those references on the PDF of the talk, which will probably appear on the Newton website. So I started this type of work on evolving finite elements with Gerd Zuck. This is Gerd Zuck, and in 2003, I was the principal organizer of a program challenges in computational challenges in PDEs. And we started working on evolving surface finite element methods in this program. There's Dr. Stiles, who's here in the audience. There's, who else should I mention? John Barrett. There is Ralph Kornhuber, who's here at the moment. And there are other faces. Oh, and John Mackenzie is here. There you are, John. 12 years ago. So there's been some evolving domains in the and evolving surface processes, by the way. Maybe, sorry?
The pictures are up here.
The pictures that's outside the Newton Institute.
That's right.
That's outside the Newton Institute, and this was a picture taken for this workshop, numerical methods for free boundary problems. Last year there was a program on free boundary problems, and I show this picture. It shows the evolution of the quality of the camera at the Newton Institute. That's one thing that it does. But also, I wanted to point out Amal Alphonse. I will talk in a moment about his work on the analysis of PDEs on evolving domains. Here's Tom Ranner. He's here. He's just arrived today. He's worked on evolving finite element method theory. Here's Hans Fritz, who just introduced himself, and here's Shaker, who's again, he's here this weekend. Bjorn Stinner is going to be giving a talk later on this week, and he should be mentioned because so a lot of the work that I will describe is joint with these people, even if I don't mention their names but you can find it in the references. This is Shaker, a few years ago, I guess. Another evolution. There's better one of Tom Ranner, and this is Hans Fritz in his James Bond mode. Excuse me. Anyway, so let me just say something about a linear partial differential equation. And this is a cartoon. We can think of this. Our domain is this curve, gamma 0. It could be a surface. So that's the initial domain, and this curve is evolving. So we want to solve the PDE on this curve. But you can also think of this as being a closed surface as well. And you can see that so in this picture here, the PDE that we're solving is on this surface. Okay, so it's a space-time surface, and this is the way that I've shown. In your imagination, n can be bigger than 1, but this is n equals 1. Formulate a PDE, well-posedness theory, numerical analysis. Conservation law on a surface. We do this balance in the standard way, but now remember this domain, this subdomain here is moving in the normal direction, moving normally. You use the transport formula, then you're led to, basically in the standard way, we're led to this equation here. Here, by this derivative, I mean the normal time derivative. I mean that it's the time derivative of the scalar on a curve moving on the domain. So it's basically this term here, ut plus v du by du, though we can't really write it like this. This doesn't make any sense because u only lives on this surface, so we can't take a derivative. Of course, if we extend u off the domain, then we can. And anyway, so the equation looks like this, and this is the conservation law. And in particular, if we take a diffusive flux coupled with a tangential advection velocity, so here this is your physical velocity, which is transporting the scalar, then the flux looks like this, and will then lead to this advection diffusion equation, where this is now the material velocity, taking into account the normal velocity of the surface and the physical material velocity. If this is 0, but still this equation is the heat equation or diffusion equation on a moving surface. So now we're going to go into some functional analysis. I'm taking a big brave step here with the audience, but just bear with me. I'm just saying this is the kind of thing that we do as mathematical analysts. So, and this equation actually looks like, can be thought of like this. So there's our material derivative, there's our differential operator, and this might be some right-hand side. U belongs to some space, it's a Hilbert space V, and we think of this equation holding in its dual V star of t. And if we do our standard thing in finite elements, people might know that you take the partial differential equation, multiply by a test function, integrate by parts in the second derivatives, or whatever spatial elliptic operator there is, how many times. If it's a fourth order, you integrate by parts twice. In the end, you get a variational form like this, which we write down in this duality pairing between V star and V, and A is some bilinear form coming from this operator here. So these spaces, V, in effect what we have are time-dependent function spaces. This is a bit unusual because we want to look at time-dependent domains. The domains are changing, so we have to do some functional analysis. And what does u dot mean in this abstract setting? Under what assumptions on A does this equation have a unique solution? What kind of problems can we apply this abstraction to? And why is it important for numerical simulations? Well, we can apply this to this diffusion equation that I showed you a moment ago. And from the point of view of, suppose that we're able to solve this in some satisfactory mathematical way, analysis way, then we're interested in using this formulation here to give a numerical method. And the standard way of getting a numerical method by the finite element method is to create these approximate function spaces based upon the discretization of the domain. So in effect, we replace these spaces here by finite element spaces. We replace our u in these abstract spaces by our finite element functions, and this would give us a numerical method. And then we can analyze our numerical method using the same kind of methods to analyze this equation here. So that's why it's important for numerical simulations. They give very, very nice numerical methods. And if we're able to do this, we kind of remove a lot of ad hocery in discretization. Oh, what time is it? I'm going to go very, very quickly. In order to be able to do this, we need to define these function spaces in a nice way. And it's quite useful to say that our domain gamma of t can be thought of as coming from gamma 0 at time t equals 0 by this flow mapping. And so we create these push forward and pull back mappings. This is a pull back. This phi would be a push forward. And from the mathematical perspective, we can now define what we call these Bochner spaces. So this is for the mathematicians in the audience. We can rigorously define Bochner spaces, and we can define some smooth functions, and in the end we can give a good definition of a material derivative. The material derivative is that we take our function and we pull it back to the reference domain, in this instance the time t equals 0. Then we can differentiate that, because now that's a standard function space, and then we can push forward. That is this, which we all know and love in this instance. The point of doing this abstraction is that we can now use this in different settings. If we're going to do mathematical analysis of nonlinear evolution equations or evolution equations, it's useful to note to have a definition of weak material derivative. And this is the definition of a weak material derivative. And there's this extra term here which doesn't occur in spaces which are time independent. And this is because when we take a time derivative of something like this, we have to differentiate this, we have to differentiate this, we have to differentiate this. Differentiating this, in effect, gives this bilinear form. This allows us to do integration in time. At the end of the day, if we're able to do what we can do all this, and we can mimic the existence theory for linear parabolic equations on time-independent domains. And then if our this comes from our elliptic operator, and these are now the standard assumptions about this bilinear form, which will allow us to use Lax-Milgram or Galerkin approach to prove existence and uniqueness to this equation. And this is a kind of assumption that we make upon the term which comes from taking a time derivative of the L2 in a product, or the H in a product in the abstract setting. So why do I want to do that? Because I can do it for the surface heat equation. So you might as well, if I'm only interested in the surface heat equation, why bother with all this abstraction? But in any case, it does apply to this surface heat equation. So just to show explicitly how we get this bilinear form here, we take, this is uv and L2 gamma of t, so we pull it back onto gamma 0, and of course we get this determinant. Now when we differentiate this, we differentiate that, and we see that we take the time derivative of this, and lo and behold, we get the divergence of the velocity. And so this term, in this instance, is simply the L2 in the product weighted by the surface divergence of the velocity. And our weak form for the surface heat equation is this, and it will satisfy all the assumptions on that we needed in the abstract setting, and we have a well-posedness. But we can also do this for bulk equations. Bulk equation. So I've chosen a flux which is, again, this has an advective term and a diffusive term, and the equation looks like this. At the end of the day, I have this W here is a velocity associated with the parameterization. And we find that the material velocity B, in this instance, combines with the tangential parameterized velocity to give this term here. And so in effect, the bilinear form we look at is this, and again, this satisfies the assumptions. But in this same kind of abstraction, we can now solve PDEs, which is a coupled surface bulk system. So here's a parabolic equation. It's in the bulk domain. It's coupled to a quantity which is advecting and diffusing on the surface, and in this instance, I'm saying that the flux from the bulk to the surface satisfies this equation. So this kind of model is appropriate for ligand receptor modeling in moving cells. This can be put into the same abstraction. Putting it into the same abstraction means that we can use the same kind of finite element analysis for all of these equations. Here's another equation. Here's Laplace's equation in a bulk domain, let's suppose that it's the boundary condition on its boundary is this kind of dynamic boundary condition here. And if we look at this, we can see that the normal derivative can be written as a Dirichlet to Neumann map. And so the equation can actually be written like this without reference to the domain omega. And there it is. And again, this can be put into the same framework. So we can generate numerical discretizations of this system in a natural way by the same process as we can for solving the heat equation.
Charles, could you comment on this pullback, the mapping? You have
Yeah.
a mapping, I guess.
We never use, sorry, in the numerical method, discretization, you never use it. It just exists simply because we have the velocity of the parameterization. We know it exists, but we don't use it except as an analytic tool.
Sure.
And so in the computation, you have a triangulation at one time step, and then you have a triangulation at the next time step. And you assume that you know the velocity of the nodes. And in some instances, you have to calculate the velocity of the nodes. But we never solve on this reference domain. You always solve on the physical domain. So you never see this pullback map in this setting. So we end up with equations like this in the abstract form. Oh gosh. To do analysis, we have a finite element approximation on an approximate domain, and we want to compare the finite element approximation to the solution of the PDE on the real domain, and that's not easy. Is anybody who's ever thought about this? If you've got a few, they're not on the same. Your solution doesn't lie on the same domain as that which you're approximating. In the analysis, what we can do is we can take these are two triangles. They're flat triangles. Our numerical solution is based upon, let's say it was piecewise linear finite elements. It's defined by its value here, here, and here, and here, of course. We can lift the finite element function onto the smooth surface if we make the assumption that the triangulated domain is within a small distance away from the real domain. That is useful because it gives us finite element spaces on our real domain, and we can compare the solution of our partial differential equation to our finite element approximation using this lift. I'm just pointing this out just to say that when we're doing this numerical analysis, there are things that we do which are elegant from the point of view of mathematical analysis, and we just have to do it. It's not just a question of throwing down finite difference scheme and sticking the thing onto a computer and hoping for the best. One has to do some mathematical analysis if you want to solve hard problems. Anyway, we also have concepts of discrete material derivative because we have a discrete surface. Furthermore, we have a discrete material derivative on the smooth surface which is induced by this lift. So that we have a decomposition of the smooth surface which is defined by this triangulated surface. That gives rise to a different discrete material velocity. Okay, so I better not. The upshot is that this is our abstract. As I said, we had an abstract formulation, and now can we replace u by a finite element function, a test function by a finite element test function, bilinear forms by discrete bilinear forms, which are natural approximations of given by the triangulation, and the upshot is that we get systems of ordinary differential equations, and it does not explicitly involve the velocity of the surface. in this formulation here. So as long as we know where the surface is, the discrete surface is, we never use the velocity in this discretization. This stiffness matrix just depends upon the surface. This mass matrix just depends upon the surface. Of course, to calculate the surfaces at gamma n plus 1, say, then you need to have the velocity. And as I said, we can move the vertices of the triangulation with an arbitrary tangential velocity, and then we get something called ALE SFN. So I just wanted to say something about moving mesh generation. So basically, we would like to think about tangential velocities, which are not going to be arbitrary. The analysis allows them to be arbitrary, but what we would like them to be able to move in a tangential direction to resolve features of the solution of the PDE, and for error control, and to resolve geometric features of the domain. This is usually in the case of the evolving domain with complex boundary. So recently with Hans Fritz, we've developed some method which is based upon geometric partial differential equations to find a good tangential velocity. And this is based upon a harmonic map heat flow and something called the Dieterk trick, and it uses a base triangulation of a manifold or submanifold. We use a normal velocity to define this manifold, and then we use a tangential velocity to find a base parameterization. That tangential velocity might not be very good. It might be the physical tangential velocity. We want to improve it. We improve it by some method based upon the harmonic map heat flow and Dieterk to compute a new parameterization. I've shown you this one before, and I won't show you that again. So this is simulation of mean curvature flow for a dumbbell, and the point in this is a closed surface, and the point about this simulation is that the shape of the elements is good. The shape of we don't have degeneration of the shape. If we find that there is a large element appearing, then we can refine and still maintain mesh quality. By mesh quality, we mean in this setting the ratio of the inscribed circle to the circumscribed circle. We like to remain that to remain constant. What we don't want are triangles which develop very small angles. So this is the disadvantage or advantage of using direct discretizations of the evolving domain. There's a topology change in this flow, and we're stuck. If we use a phase field approximation, the phase field approximation will produce two domains. And then the big question is what does the phase field approximation mean? So it's an advantage and a disadvantage. If we use phase field, then it's often the case. There are results which show that there are results which give you rigorous approximations, but they're usually to things like mean curvature flow. Okay. So this is what I mean. This is an example which shows a bad mesh by using a not very good definition of tangential velocity. So there's no partial differential equation here. This is just the generation of a mesh for an inclusion which is moving in this rotating way. I know it's moving slowly, but now you can see the problems with the mesh, and actually there may even be mesh entanglement. That is, the vertex of an element might suddenly find itself in the interior of another triangle. In the interior of a triangle. So use this new algorithm. This new algorithm produces meshes which are much nicer. Actually, they're quite beautiful mesh. It's a beautiful mesh because the vertices of the triangle, vertices of the triangulation, come from solving a partial differential equation.
So you have adaptivity, mesh adaptivity.
This is not mesh adaptivity. There is no mesh adaptivity here. Well, there is, but The concept that I've just been speaking about is just taking a mesh and finding a good velocity which preserves the shape of the elements. If you don't like the shape, if you don't like the size of the elements, they might be too small, they might be too large, then you can refine and coarsen. So that would be mesh adaptivity. You can refine and coarsen as you like, but if you have a good mesh quality, then you can refine and coarsen and maintain the mesh quality. If you've got a lousy mesh quality, you're done. Then you have to retriangulate. So that's the virtue of this scheme. Right. So I've kind of really went very quickly through the mathematical analysis, and I'm just going to go quickly through numerical analysis. So this is numerical. So there's a power h. There's a power 2 here. This power 2 is because the way I've written this analysis is for piecewise linear piecewise linear function spaces. And yeah, recently with Tom Ranner, we've generalized this approach to higher order finite element schemes, so we can replace the 2 by k plus 1, where k is the order of the finite element scheme. Anyway, so the analysis is based upon this is a perturbation analysis. So we can take our finite element function and we can lift it onto the domain that we're approximating. Then we would like to relate this thing which we compute to something which we're never going to compute, but which we're going to use to do the analysis. So this is a geometric perturbation, so we need to do this. We need to do this analysis. Similarly, we have a continuous velocity, and then we have a discrete velocity, which has come from the decomposition of the smooth surface by this underlying triangulation. We have to analyze that. And then that means that we have to consider the difference between a continuous material velocity and a discrete material velocity. There's lots of different things that we have to do in the analysis, in the mathematical analysis. When we compare the solution of the finite element solution and the solution of the PDE, there's a very, very nice thing that simplifies analysis for time-dependent problems, which is to use an elliptic an elliptic estimate. And this is analyzing the approximation, finite element approximation of an elliptic problem. It's in this instance we call it the Ritz projection. We have to analyze the error and the error in the material derivative of the Ritz projection. So there's quite a bit of work in that. Then we take the error and we decompose it into 2 parts. One which is we can think of as to do with the approximation error, which is the difference between the solution of the PDE and the Ritz projection, and that which is to do with discretisation. It's to do with consistency, and we can rewrite the finite element equation like this. We get a finite element error equation, and we find that this looks like our PDE, but we've got a right-hand side which is a perturbation. So we want to estimate theta in terms of the perturbation on the right-hand side, and that's basically the method of error analysis. And the upshot is that we can prove that the error in the solution is of the same order as the approximation. Well, we can do that for more general finite element spaces, and in this abstract setting, although I kind of did this in the context of the heat equation, this analysis holds for all of those equations that I described, provided we can construct the finite element spaces. Okay, and this can also be done for time discretisation.
So your right-hand side, the F.
In that instance,
you are treating it as data. Are you or
this is analysis. This is nothing to do with numeric. This is nothing to do with computation.
No, I know.
This is analyzing the error. So this is all of this is perturbations which should come from all of the geometric
No, but in your PDE you have the right hand side, which is a function f.
Yes.
And this is the function I'm talking
Yeah.
about. So
Yeah. Yes. What's your question?
what is it really? I mean, does it have to satisfy some properties, I guess? Or,
This?
Or
Oh, I see.
Yes.
You want me to look at a different equation. Shouldn't have done this. You want me to look at a different equation. You want me to put a right-hand side into the equation. This F.
Right. Or,
This is a trivial. This is a trivial perturbation of what. This is not. This is. We can put in a right-hand side here, and the analysis and the numerical method is complete and absolutely straightforward. And in the analysis of the error, this would just lead to another approximation error, an F3 or something like this, which would be of the appropriate order.
right.
It's not an issue. It's not an issue computationally, and it's not an issue. It's not an issue from the analysis perspective.
I would assume this is independent of the solutions. Your right hand side is independent of this.
If you want, this is a model problem.
Yes,
We can use this idea for solving nonlinear equations. That's not what I'm talking about
Oh.
here. And if you want to solve a nonlinear equation, then there are other things that I could put into this. I'm finishing on time by doing things rapidly. So I've shown you some simulations of meshes. Here is another cartoon simulation of which is based upon solving a geometric equation coupled to a reaction diffusion system. So in those simulations, we're solving a fourth order equation for the curve, and there's a kind of a protrusive force which is obtained by solving a reaction diffusion system. And if you go to John Mackenzie's talk later this week, I think you'll see other simulations like this, and there'll be more a better description of the model. Okay, and of course we can do this in we can do the similar thing for surfaces. Again, this is just a cartoon to show that one can simulate solutions of PDEs in complex domains by directly using evolving finite elements. And again, this is another cute thing, which is just passively pushing away those. What are they? Shaking. What's it pushing away?
I think the red blood cells.
Yeah, they're pushing away red blood cells. Okay, that's this famous 1952 video you can find on YouTube. And this is chemotaxis, and where they're all looking to try and get hold of that food. And so there's a gradient, chemotactic gradient, which is pulling them to, and one of them succeeds. Yeah, this is another cartoon. This is just to show that what's possible. It's not supposed to be a good mathematical model of anything, but in effect, it's again we're computing the solution of the surface PDE and a nonlinear equation on the surface, and it's okay. This is its way. That's its target. It's moving on a rough surface. Okay, I've come in on time. Good.
Questions? I will start with Christian.
Of course, it's more a modeling question. whenever you want to have any transport phenomenon or anything on a moving surface, you always need this physical velocity, right?
Yes.
You need to know where material points on the surface go.
Ah, yeah, yes.
Right? So the question is,
Yes.
is there, so the main question for me in this business is, for applications, is how to find this.
Well, how to model it.
How to find, yeah.
No,
how to
I
find
mean,
material.
how to model it.
Yeah.
Once you've modeled it, you've got an equation, and then you can find it.
Yes. Yeah.
That's the way that I would like to
So,
say
but
it.
no, my question would be, you showed this phase separation example, for instance.
Yes.
And there you have this, right? You have diffusion on the surface and reaction. So
Yes.
You need it there in order to. The question is, what did you do? Well, you
Okay.
talk about diffusion on the surface. Whenever if you just talk about diffusion, you need to know where the material goes, right? Otherwise,
Oh,
what does
in
diffusion
that
mean? Yeah?
There was no tangential velocity in this. There's no material tangential velocity in that simulation.
So these there always the assumption was that the tangential physical velocity is zero.
Correct. In that example, the only physical velocity was in the normal direction. The mesh had some arbitrary tangential direction, which was modeled computationally handled in the correct way, and it was based upon an algorithm of Barrett-Garth-Nurnberg. That was done some years ago, and the work that we've done with Hans simulations, which we show, would give maybe give it some improvements on that aspect of generating a good mesh. But another response I can make to your question would be that you now have the possibilities of computing solutions to the Navier-Stokes equations on a moving surface. So that's the next. That will be the several steps that you could think about now. You can think, if you wanted to use evolving finite element spaces, you would first of all you would want to solve the Stokes equations inside and outside. Then you might want to then put the Stokes equations or Navier-Stokes equations on the surface and do this coupling. Okay, so this is a big, complicated system, but what you have is a way of generating the mesh. What we have is a way of generating the meshes in a nice way. Of course, people have done these simulations using phase field methods. So I don't know whether there's a talk on the phase field method for this later on this week, but there was in July. John, yeah?
When you have problems where part of the solution process is to find an unknown surface, and part of the solution process is to find solutions of PDEs on that surface, what's a meaningful way of characterizing the error?
Well, that's a very good question. I don't know. I can't answer that question, actually. Can't answer that question. Well, I'd quite like to answer this question first. Can we prove convergence of surface span for geometric PDEs? Well, we can for curves, but we can't do it for surfaces. Kind of related. I don't know the answer to your question. Yes? Sorry, I was looking. This person was first, and I asked.
It's okay.
Am I sharing?
Don't worry.
This is what happens.
Yes. Yeah.
I'm so used to chair.
Yeah. Go ahead.
Actually, by changing, by moving the vertices,
Yeah.
you don't mean that we move the material.
Correct.
Correct. Yeah. So if we have, for example, a non-uniform domain, and we have a mesh in a non-uniform domain.
Yes.
So when you move the vertices, the mesh doesn't keep a constant property. Because you're moving
Take a fixed
mesh
domain.
over a constant material which is not uniform.
I don't know what you mean by uniform.
I mean, suppose that I'm doing mechanics, so I'm always thinking about a material which doesn't have constant mechanical properties. Suppose
Yes.
some parts of it is
Fine,
software,
fine,
some parts.
fine. Yeah. The mesh is completely independent of the solution
Yeah.
of the PDE.
Yeah. So suppose that one element is
Yeah.
was previously in
Yeah.
a soft domain.
Yes.
Now you are moving the vertices, and
Yes.
now the same element
Yes.
is located in a place that half of it in a stiff domain.
Yeah.
So these.
This is a question of nonlinearity.
Yeah,
And
and
it's a-
is
you have to-
taken care of in your differential equations. I mean,
I think this is a
By
this
itself.
is a question of nonlinearity, and I think well, we have solved nonlinear PDEs on moving surfaces. So I guess
I think
This
we
is-
just need to make sure the PDE is written in a conservative form.
That's fine.
that's
Then this issue doesn't arise.
you certainly have to write your PDE in a sense in a what I would call in a way in which you have the possibility of proving well-posedness of the PDE. And if you do that, then if you use a sensible, a consistent finite element approximation to the variational form, then hopefully things would work out. But I would need to look at your particular problem to understand what really actually means.
Would there be any difference between an interface between two surfaces that literally had no thickness, or it was constant and infinitesimally small, and one in which you seem to be pointing to, you not only have a moving surface but a moving thickness or changing thickness to the surface? Would it affect anything you've said?
Yes, it would. In one sense, that's an interesting question for the mathematics, because you can think of this. You can think of taking this. Suppose I had just consider a partial differential equation on a moving surface. Now thicken the surface, and think of a way. Now think that actually I quite like. Don't want to use surface finite elements. I want to use standard finite elements. So I thicken the surface, and I consider an appropriate equation in this thin domain. So let's suppose the thickness was epsilon.
Yes.
Think of the thickness as epsilon, and then if you write down your equation in this thin bulk domain in a sensible way, and of course sensible means that you write it down, it's consistent with whatever physics you've got, then the question would be, as epsilon goes to 0, can you prove the solution of this thin domain converges to the solution of the surface PDE? And there are results like this in the case of stationary domains, many results, and now there are results like that for moving domains. Furthermore, from the point of the numerical approximations, people quite like this approach with respect to phase field methods. If you do a phase field approach, it's quite likely that what you will get for the approximation of the surface will be a thin region of width epsilon. And then maybe then a natural numerical method will be then to use a bulk, what I call bulk finite elements, if you like, for solving this equation. And there are methods of that kind as well. So.
I asked the question partly because you had that beautiful picture where you had a thin filament and you said it was changing the topology of the system. And I just wondered whether that was going to break or not, and whether you had a...
It breaks. It breaks from the point of view of the what we would call a rigorous theory of weak solutions to motion by mean curvature. Then it breaks, and if you were to use a phase field method, then you can approximate all through the singularity. And if you use something called the level set method in that particular instance, you can also do the same thing. And for motion by mean curvature, there is a rigorous connections between these. But for more complicated evolutions, then this connection has not been made, and that is, in fact, it seems to me, one of the big problems in evolution of interfaces is how do you deal with merger and breakup. Of course, it's almost like an internal problem, It's a question really of physics, because you really need, I think you need to know what the physical model is, the breakup or merger. And relying on numerical methods which don't have physics but actually produce merger and breakup is kind of problematic, I think. Phase field seems to be the best way to go at the moment for that kind of computation.
One last question, if we have any. Yes, Jocelyn.
Well, rather technical question. So you mentioned the lift between the approximated mesh and the exact surface. Is there proof around of the one-to-one mapping between the two?
Yes.
Okay, so I'll ask you for the reference, because I haven't found it yet. And also since you're using, well, if your mesh is now set-vectored with the physical velocity, then the solution, whatever, needs to be transferred to a mesh which is not consistent with it. So you need to interpolate a solution which is not smooth, which is a finite element approximation, onto another mesh. And I'm not aware also of error control on that. For instance, a piecewise continuous solution, and you want to approximate it with a mesh which is not matching with the places where there's discontinuity in the derivative.
In of course, in ours, they do match because we have underlying a discretization of a smooth parameterization. So our gamma n plus 1, which is but if you were to use, if you wanted to do, I think the question is to do with coarsening and refinement on.
That's another issue in which it rises. Already having a velocity of the nodes which is not a material velocity means that you have
there is no need in the way that I presented this, the velocity of there's no issue with respect to the material velocity and the velocity of the nodes, as far as I'm aware. Of course, there is always the possibility of considering a more complicated PDE and introducing all sorts of effects, so I would have to. I can't answer your question.
Right, let's thank our house again.